Okay, so yan. F5. So just a brief recap of how to handle page faults, no? Okay, so this one is the idea of page replacement. So this figure shows that, for example, there are two processes in the memory, and you have the page table for this process and page table for this process. The program counter or the instruction pointer is at this point, load M. So what will happen is when this instruction gets executed, it will look at the page table, is M in the memory. Wala pa siya. Okay? So what will happen is magkakaroon ng page fault, and this M has to be brought to the memory kasi kailangan siya ng instruction na to. Okay? This is the current process that is executing. So what will happen is, since full yung physical memory, okay, there is a need to replace, to select a page here to contain this page required by the running process or by the instruction. Okay? So the page replacement algorithm basically has this structure. Okay? So you swap out, dito yung kanina dalawang disk ayaw ang gagawin. So you have to swap out the victim page and then swap in the desired page. Okay? And then you have to update the page table accordingly. So in the page replacement, there are two things that you need to consider. One is frame allocation, which determines how many frames to give each process. So you have demand paging. You run a program ./hello.exe. The operating system will load that program into memory. How many frames are you going to allocate for that process? Okay? Now the other problem or the other issue is page replacement algorithm. So there is a performance degradation when you use demand paging because of the disk I/O. So what you want to minimize is the page fault rate. Right? You want to minimize the number of page fault whenever you execute a program. So that is the two issues that must be addressed when it comes to page replacement. Right? So in the study of we start with page replacement algorithm. So we actually just use a reference string which indicates these are the page numbers, right? That represents the pages that is accessed or that are needed by a particular process. So you are given a sequence, a string of page numbers, and you are also given the number of frames, right, for this study of the algorithms. So as I said last time, ideally, if you increase the number of frames, the number of page faults decreases. Because essentially, kumbaga, there are available slots in the main memory that you can map the page to the frame. So as you increase the number of frames, the number of page faults decreases. So we discussed the first in, first out algorithm. So basically, the idea here is, okay, the process reference this page number. It is not in the main memory, so generate a page fault. So this figure here illustrates one page fault because 7 is not yet in the main memory. 0 is not yet in the main memory. Generate a page fault and then load 0 in the main memory. Then 1 not in the main memory. Okay, place that in the main memory. That's one page fault. 2. Okay. Now 2 here, when the process reference page number 2, there is a problem because all the slots in the main memory are occupied already. So this is where the algorithm, the page replacement algorithm, will kick in. Now using the first in, first out, since 7 is the first page number that was mapped to the physical memory, this is the slot where the new page will be placed. So 2 is here. Then you have a reference to 0. Now 0 is already in the physical memory, so there is no page fault that will be triggered. So it's empty here. Then 3, okay, and 3 is not in the main memory. There is no mapping, so you have to select a victim page. So since this is the last one used, so you replace that. So essentially you have this. And you count the number of page faults, you see here that you have 15 page faults. And Belady's anomaly actually is an example that although if you use the first in first out page replacement algorithm, even if you increase the number of frames, it's also possible that the number of page faults will increase. So as shown in this graph, so the trend of the page fault, number of page fault relative to the number of frames without Belady's anomaly, it should be going downward. However, at this point, if you have 4 frames, given the reference string, you'll get something like this, the number of page faults, by 10 page fault. Whereas supposedly, this is already 9, you're hoping that the number of page faults, since you have 4 frames, should be 8. However, using the first in first out, it suddenly increased. The number of page faults suddenly increased. So that's the problem. So the optimal algorithm is to replace the page that will not be used for the longest period of time. Okay, so this allows the main difficulty of this is you have to be able to look into the future, determine which of the pages will not be used for the longest. Hindi mo talaga gagamitin. Okay, so this is an example. Given the original reference string presented in FIFO, so you have 7, place that page fault, 0, page fault, 1, page fault, 2. So 2 is not in the memory, right? So you have to determine, you have to go forward in the future, determine which among these 7, 0, 1 will not be used for the longest period of time. So if you scan the reference string, you will observe that 7, malayo pa siya masyado bago gamitin. Diba? So the optimal is to select 7 and place 2 there. And 0 is here. You get the idea of the optimal algorithm. However, the problem with this is, of course, there is no way to look into the future to determine which page will not be used for the longest period of time. So we need an approximation. And that approximation is called the least recently used algorithm. So instead of looking forward in time, you look backward. You determine which page has not been used in the most amount of time. Yung laging hindi ginagamit, so tanggalin mo na yan. It's like just like I have a bookshelf and I have a set of books in the shelf. Since maliit lang yung shelf ko, 2 layer yung books ko. So ang ginagawa ko, yung mga hindi ko ginagamit nandun sa loob, yung nasa labas yun yung mga books na easy access. So that is the idea. And to do that, you need to associate a time of last use with each page. So whenever a page is referenced, there should be a support or a hardware bit that indicates when that page was last used. Okay? So going back to the example reference string, so you have the reference string. So again, you have page faults, and what will happen is you try to determine, you look back in time, alin dyan ang mga hindi ginagamit. So parang ang assumption dito, if you're not using that, if you have not used that page for a long time, probably you will not be using it in the future. So that's the idea. So using this LRU, you generate 12 faults, which is greater than the optimal but less than the FIFO. Okay? Now the question is, how do you implement this? Because you need to associate the time of last use within each page. Okay? So there are several implementations for the LRU. The first one is the counter implementation. So you have here a counter for every page entry. Okay? So kumbaga may clock ka dapat, tapos ilalagay mo yung for every memory access, kukunin mo yung time ng pag-access na yun, tapos ilalagay mo dun sa page, okay? as a data structure. Okay? So when a page needs to be changed, look at the counters to find the smallest value. So yung pinakamaliit na value dun sa counter, ibig sabihin, yun yung hindi ginagamit for the past few memory accesses. Yun yung i-replace mo. Right? And this will require a search through the table. So if you perform linear search, that will be O of n, where n is the number of entries in the page table. Right? Now another implementation is the stack implementation. So here you keep a stack of page numbers in a doubly linked list form. Right? So you have a stack of page numbers. When a page is referenced, right, is accessed, you move it to the top. Okay? And basically, so ibig sabihin, yung nasa top, yun yung laging ginagamit na page. Yung nasa ilalim ng stack, yun yung hindi ginagamit. So when the time comes to determine which page to replace, you simply replace the page that is at the bottom of the stack, because that is the page that has not been accessed for a long time. Right? Now, it will require 6 pointers because you have to be able to move up a page to the top of the stack. Right? So that's one. So LRU and opt are cases of what they call stack algorithms that don't have Belady. So again, there are two implementations for LRU. You have counter implementation requiring a hardware support, and stack implementation using data structures, stack, and a doubly linked list implementation. So here's an example of the reference string. So 4, you push that on the top of the stack. 4, 7, 0, so etc. So at this point, stack before A. Okay? Ito yung laman ng stack. Okay? And then 7, kailangan mo na ngayong magtanggal. Okay? So you replace the one on the top of the stack. The idea. And this is the so use of stack to record the most recent page references. So ilalagay mo sa taas yung laging ginagamit. Okay? So LRU needs special hardware and is still slow because of the data structures. So you need some approximation. Right? So because not all architecture support this implementation, especially this one, you have the counter. So you try to approximate that with the existing hardware available. Right? So we usually have a reference bit, right? With each page we associate a bit. Initially set to 0, and when that page is referenced, that bit is set to 1. Right? You replace any with reference bit 0 if one exists. Right? So basically you have to look at the reference bit. Kung 0 siya, okay, siya yung mga i-replace mo. Right? Kasi hindi siya ginagamit. Right? And the second approximation algorithm is called the second chance algorithm. Right? So basically FIFO din siya, pero once na since may reference bit ka na, okay, pag may nakita ka na 1, hindi mo agad siya i-replace. Bibigyan mo siya ng second chance pa. Okay? So if page is to be replaced, okay, kailangan pag yung reference bit niya ay 0, replace it. Pag reference bit niya ay 1, okay, skip mo siya, and then sa next round mo na lang ngayon siya i-replace. Okay? So here's how it's done. So you have a circular queue of the pages. Ito yung reference bit. So sabi dito yung reference bit, right? Initially set to 0. When page is referenced, you set it to 1. Okay? So sa second chance algorithm, right? So 0, 0, this is supposed to be the next victim kasi 1 siya. Okay? Kaso, hindi mo siya i-replace agad. Okay? Hindi mo siya i-replace agad. You simply set that to 0 and then move on and find the next. Yun yung next na i-replace mo. Okay? So you give that page a second chance. Right? So we also have an enhanced second chance algorithm. What it does is, kasi dun sa default na second chance algorithm, ang ginagamit mo lang doon ay reference bit, only one value, so 1 or 0 lang yan. Okay? But in the enhanced second chance algorithm, you use the reference bit and the modify bit. Okay, dalawa. So pag 0, 0, neither recently used or not modified is the best page to replace. So yung first ay yung reference, yung second yun yung modify bit. So depending on the values, okay, the combination of the values of these two bits, so apat na yung possible values, then that is the you base the criteria based on these values. Okay? So when page replacement is called for, use the clock scheme, but use the 4 classes to replace the page in the lowest non-empty class. Okay? So that's basically the idea. There are other algorithms for page replacement. So you keep a counter of the number of references that have been made to each page. So again, kailangan mo ng additional data structures. Okay? So you have first the least frequently used, LFU. Okay? So given the counter, you replace with the one with the smallest count. Okay? And then the other one is the most frequently used algorithm, which is based on the argument that the page with the smallest count was probably just brought in and has yet to be used. Okay? So you don't replace that. Okay? So are there questions? So you just write your questions on the paper. Okay. Page buffering algorithms. So I hope that you can follow. No? So we're talking about virtual memory. So yung page replacement algorithm, ang purpose nun is to determine how do you select the page to replace. We discussed different algorithms, and the best way to implement is LRU. However, LRU is difficult to implement because it requires hardware support. So there are approximation approaches to do that, like using the reference bit and the modify bit. Okay? So page buffering also is important. Okay? So instead of every time na magkaroon ng page fault ay kailangan mo mag-access ng disk, parang equivalent ng TLB. Okay? So you keep a pool of free frames always. Then frame available when needed. Okay? So ilalagay mo lang doon. Okay? Doon sa free frame na yon, para hindi mo na kailangang mag-swap out. Doon mo na kukunin. Before ka mag-swap out, available na agad. Hindi ka na magsa-swap in pa. Na-minimize yung disk. Nandun na dun sa parang buffer ng free frames. Okay? So when possibly keep list of modified pages. When backing store otherwise idle, write pages there and set to non-dirty. So parang nangyayari lang dyan, ipi-pre-read mo na yung mga pages para hindi mo na i-read siya next time na magkaroon ng page fault. Okay? So that's the idea of page buffering. Okay? Again, for performance enhancement. Okay. Other issues with the page replacement. Okay? So yung page replacement, again, is implemented in the operating system, kernel. Right? And for some applications, like databases, okay, ayaw na nilang gumamit ng page replacement algorithms na ginagamit na pinoprovide ng operating system. Okay? So all of these algorithms have OS guessing about the future page access. So some applications have better knowledge, like databases, and anong ginagawa nito? Perhaps you have not encountered this, but if you've used Oracle, kung gagamit kayo ng database na Oracle, may SQL kasi kung ano yung default na pinoprovide na page replacement algorithms ng host operating like Linux, yun yung gagamitin niya. Yung Oracle is a powerful database and medyo advanced siya. Pag in-install mo siya, i-require ka niya na mag-create ng tinatawag na raw disk. Okay? Parang equivalent siya na unique file system na hindi siya traditional na file system na provided ng operating system like NTFS or ext3. Okay? So meron siyang tinatawag na raw disk kasi yung pag-read niya ng data, alam niya yung access patterns ng data, so it doesn't have to let the operating system do that for the Oracle database. So if ever in your job, maging database administrator kayo, when you install Oracle, you will have to specify what you call a raw disk or a raw partition. Okay, so this is the part on the page replacement. The next one is allocation of frames. So dalawang issues kanina ang na-mention. Frame allocation, how much frame to allocate for a process, and then page replacement because we have demand paging. Okay? So each process needs a minimum number of frames. Right? So it's usually dependent on the architecture. In the case of the IBM, okay? Siyempre, kumbaga, at titingnan mo dyan, ano yung worst case? In the case of the IBM 370, an old machine, okay, meron siyang tinatawag na SS move instruction. And this SS move instruction will require 6 pages. Okay? So, ibig sabihin, at the minimum, when you have a process that runs on this particular machine, you need to allocate to a process at least 6 pages para hindi siya mag-trigger ng page fault. Okay? So, once niload mo na yung process, meron ka na dapat na 6 frames, 6 pages na pre-allocated sa kanya. Okay? The maximum, of course, is the total frames in the system. So, of course, pwede mo lang i-allocate lahat ng available frames for that process. However, siyempre, we want to improve or to increase the degree of multiprogramming. So, hindi naman rin i-allocate lahat yon. Okay? So, that's the ideal. Okay? Especially if you have if you have a multiprogramming system. So, there are two major allocation schemes. We have the fixed allocation and priority allocation. So, of course, there are many variations. So, yung fixed allocation, okay? So, marami kang processes. So, an operating system, isang system, meron kang space para sa kernel, meron kang space para sa user processes. Okay? So, for fixed allocation, okay, you provide the fixed number of frames to each process. For example, if there are 100 frames, okay, after allocating frames for the OS. So remember, yung kernel, lagi siyang nasa memory. Okay? Lagi siyang nasa memory, siya yung nagmamanage ng lahat. And nag-load siya ng process, okay? /hello.exe. Ilang frame ang i-allocate mo doon sa hello.exe? Yung isang user, nag-run siya ng Vim. Yung isang user, nag-run siya ng Firefox. Ilang frame ang i-allocate mo para sa process na kailangan nila? Sa fixed allocation or equal allocation, you allocate a fixed number of frames. So in this case, if you have 5 processes, you simply divide the available frames, so each process will get 20 frames. Right? And you also need to keep some frame as part of a buffer pool, tawag, available frame. So yun yung equal allocation. However, inefficient yun kasi, halimbawa yung Firefox, yung isang user Firefox ang ginamit niya, Firefox will require a lot of memory. So, pag inallocate mo sa kanya ay 5 frames lang, tapos marami siyang ginagawa, magti-trigger siya ng maraming page fault, which will degrade the performance. Okay? So, what if, since halimbawa, hello.exe lang naman yung process na niran ko, what if I allocate only 2 pages for 2 frames for that hello.exe and allocate the rest to Firefox? So, at least, in a multi-user system, hindi magde-degrade yung performance kasi hindi magti-trigger ng page fault yung Firefox process. Okay? Now, a better solution is called the proportional allocation. Yan yung sinasabi ko. So, you allocate according to the size of the process and dynamic as degree of multiprogramming. Okay? So, an example of this, let's say you have SI. This is the size of the process PI. So, meron akong hello process, yung nag-login sa server, merong Vim process, yung isang nag-login, meron siyang Firefox process na nilaran. Okay? So, bawat sa kanila merong size. Okay? And then you get the total of the sizes of the process, that will be the big S. And then you have the total number of frames. And then the allocation will be proportional. So, SI divided by the total multiplied by the number of frames. So this is an example computation for that. Okay? So yeah. So most implementations usually implement proportional allocation because this is better. Okay? Priority allocation, on the other hand, of course, there are some processes that are high priority, so you allocate more to those processes. Okay? So a process PI generates a page fault, select for replacement one of its frames. Then select for replacement a frame from a process with lower priority number. So dalawa yung option mo. Pwede kang magtanggal sa sarili mo, frame, or kumuha ka dun sa process na lower yung priorities. Okay? So, given that, we have global and local allocation. So, meron kang system. Nandun lahat yung processes. Okay? So, there are two approaches. So, ang goal din is mag-allocate ng frames sa processes. Okay? So, yung global, the process selects a replacement frame from the set of all frames. So, global, I hope that you can always visualize na yung nangyayari sa akin. This is the physical memory. Ang minamanipulate natin dito ay frames. This is the logical memory. Ang minamanipulate natin dito ay pages. Then we have the page table here. And you have the mapping. So, lagi niyong natandaan na itong relationship na to. And this is our swap. So, lagi niyong, when we talk about memory, when we talk about this, ito yung nangyayari. So, sa global and local allocation, ito yung mga frames. So, sabi natin, dahil sa virtual memory, 1, 2, 3, 4, 5, 6, 1, 2, pwedeng mas malaki yung logical memory. This is the logical address space kumpara dun sa physical memory. Nandun siya, and then kasi possible to kasi pwede yung mag-swap in, swap out via page replacement. Okay. This sa global allocation. So what happens here is when you create a process, okay, yung operating system, pag nag-load siya ng process, so halimbawa hello.exe. So, hello.exe. So, ito ngayon yung i-allocate sa kanya na logical address space for hello.exe. And, yung iba dito, pag mag-allocate ka ng frame, pwede ang mangyari, okay, kailangan mong i-populate yung page table. Okay? So, ilang frames ang i-allocate mo dito? Pwedeng lahat. Okay? So, lahat na 1, 2, 3, 4, 5, 6. So, ito yung physical memory. 1, 2, 3, 4, 5. So, pwede niyang kainin lahat yan. Okay? But if you have other processes na gagamit din itong physical memory, okay, kailangan magkaroon ng frame allocation. Pwedeng sabihin na, ito si hello.exe, dito sila mag-run. Si Vim, dito mag-run. Si Firefox, dito. Okay? If we have additional processes here. Okay, you get the idea? So, yun yung ibig sabihin. Yung global replacement, pag kailangan mong kumuha ng frame, kahit ginagamit niya ng, ito na-allocate mo to sa Vim, hello. Ito na-allocate mo sa Vim. Ito ay na-allocate mo sa Firefox. So, remember, yung kanya-kanyang process merong sariling address space. Okay? Mamaya, i-demonstrate natin. So, yung global replacement, halimbawa si hello, pwede niyang gamitin yung ginagamit ng Vim or yung ginagamit ng Firefox. Yun yung global replacement. Okay? Pag sa local replacement, each process selects from only its own set of allocated frames. So, di ba, may page replacement tayo. Okay? So, pag local, ito yung allocated sa kanya. Di ba, may frame allocation tayo. We have frame allocation. Okay? Ito yung na-allocate sa kanya na frame. Pag local replacement, pag magkakaroon ng page replacement, dito lang siya kukuha sa allocated sa kanya na frames. Pag global, pwede siyang kumuha sa iba. You get the idea? Okay. So, non-uniform memory access, and this is another issue, right? So far, all memory access are equal in terms of time. There are architectures na kung saan pag malayo yung core sa memory, mas matagal yung memory access time. So, you also need to consider that, and when you allocate memory or when you allocate frame, doon ka pipili, doon sa pinakamalapit sa'yo na memory. Okay? So, you choose the memory close to the CPU on which to run. Can you get the idea? Okay. So, siguro, demonstrate natin. Okay. Baka hindi nyo pa nakikita yung relevance ng okay. So, CD 125 volts. Okay. So, okay, so sige, unahan na natin yung okay, yung signal, ira natin yung signal. So, ECC. So, let's run that in the background. So, let's create 2 instances of this program. Okay? Para makita nyo yung anong pinagsasabi ko, right? Yung logical address space. So, if I type PS here, meron akong isang process na nagra-run, 12105. And then, if I type PS here, meron din akong isang A.out na nagra-run. They have different process IDs, 12096. Okay? So, magkaibang process sila, pero they refer to the same program. Okay? Now, if we look at the memory, okay, location, so, pasukin, i-debug natin yung 120, yung isang process na nandito. Okay. Ang gusto kong ipakita dito sa inyo is that yung dalawang process nito, ang nakikita nila, they have access to the same logical address space. Pero dalawang instances ito ng process, right, ng A.out. So, nakikita nyo yung, nakikita nyo ba? So, this is the address space of yung isang instance ng process. Okay, process 12096. And ito naman yung address space mapping ng process na 12105. They belong to the same binary. O yung A.out, yung signal. Okay? And you will notice na yung memory mapping niya, 0x4 400,000, 0x400,000. Anong masasabi niyo dyan? Pareho ba sila magkaiba? Pareho sila, di ba? So, teka, parang so, if you guess na pareho sila, are these addresses in the physical or are they in the logical address space? Patingin nyo, yung address na pinapakita dyan. Nasa logical siya, nandito siya, physical or frames, or dito sa sa logical. Nasa logical siya. Okay? So, nasa logical siya kasi ang tingin ng process na A.out sa kanya yung buong memory na yan. Transparent yan sa kanya. Akala nila pareho, they have access to this memory. Pero essentially, sa physical memory, magkaiba actually sila ng location. You get the idea? Because of this page table. Okay? So that's what we mean by that. And ito yung mga section. So, ito 400,000, nandyan yung code section, data section, DSS, may heap dapat yan, kaso wala. Pero nandyan din yung live seed, saka yung dynamic loader, tapos yung stack, nandito. So, ang tingin ng bawat process na yan, meron silang access sa napakalaking memory. Pero in reality, yung operating system nagpe-perform ng demand paging. Okay? So that's what we mean by that. Okay, so I hope na-understand niyo yung concept natin ng virtual memory. Okay? Yun lang ang isa sa mga essential na ma-appreciate niyo dyan sa virtual memory. Okay, so saan mo tayo? Okay. So thrashing. Ano yung thrashing? Thrashing is a process that does not, if a process does not have enough pages, the page fault rate is very high. Ma-observe nyo sa laptop nyo, pag masyado na rin marami naka-open na tabs or mga applications, tapos 4 gig lang yung RAM nyo halimbawa, napansin nyo yung disk nyo, very active. Diba? Maririnig, kung hindi SSD, maririnig nyo yung kalaskas ng disk, di ba? And that is what we mean by thrashing. A process does not have enough pages. Okay? So, nagpi-page fault siya to get the page, replace the existing frame, and then ibabalik na naman. Kasi wala nang wala nang available. Kumbaga, puno na to puno na yan. Marami ka pang process dyan. You can use global replacement, frame replacement, or local replacement. So, laging may activity. This activity, and that is called thrashing. And this leads to low CPU utilization, and pag detect ng operating system, low CPU utilization, i-increase niya pa yung yung degree of multi-programming. So talagang nakita mo yung disk activity mo na nagsa-swap in, swap out siya. Kaya na-experience niyo ba yan? Okay, so that's called thrashing. I hope you can explain that now to your friends, to family members. Okay. That is what happens. You increase the number of processes, you increase CPU utilization. However, at some point, dahil nga sa mayroon tayong demand paging, yan, trickle down yan. Kasi most of the time, the CPU will just be doing swapping in and swapping out, paging in, paging out. Okay. Demand paging and thrashing. Okay. Why does demand paging work? So, paano ba gumagana yung bakit pa kailangan natin kumbaga, matataka kayo. Di ba yung idea ng paging, in-split mo yung memory into fixed size block? Okay? Para, sabi natin, to minimize external fragmentation. Okay? How will it work kung meron tayong idea ng thrashing? Okay? So, meron tayong tinatawag na locality model. You say locality model, the process migrates from one locality to another. When you say locality, halimbawa, ito isang page, usually ang size ng isang page ay 4 KB. So, yung isang process, pag nag-execute siya ng instruction, yung idea ng locality is yung mga ina-access niya na memory, usually confined lang doon sa page na yon. So, if you have that mechanism, pwede mag-work na yun yung demand paging. Okay? And thrashing occurs when the sum of the sizes of the locality is greater than the total memory size. Okay, so yun yung mangyayari. Okay, so ito yung mga localities nila, then pag malaki yan sa memory size, doon ngayon i-trigger yung thrashing. Right? So here is an example, illustration. So ito yung execution time ng isang process. Ito yung page number na access, yung memory address. So, kumbaga, confined lang doon sa area na yun. Okay? Yung mga memory references nila. Okay? So that's the idea of locality in pag-access ng memory. Ma-observe nyo naman yan. So diba, nag-function call kayo sa C, nag-function call kayo. Magkakaroon ng jump instruction, tapos yung execution ng instructions will be confined to that function, kung saan nakalagay yung function na yun, di ba? So that's what we mean by locality. Pag nag-exit ka na sa function, nag-return ka na, saka lang mag-iba na naman yung locality. Okay? So halimbawa, at one point in time, nandito yung execution ng isang function, at some point, nandito naman. So that's a cluster sila doon. So that's what we mean by locality. Okay? So we'll stop here, and if you have questions, write them. And pass the paper. So I hope you understand now yung